In this video, I briefly want to go over the design of recursive data types and how you guys will be able to design your own recursive data types in the future. So here we have our classic list of data type. List of string is one of either empty or const string list of string. This self-reference over here is going to allow this data type to grow arbitrarily long, but just as importantly, this empty tells us where this list will stop growing, right? So we see the code structure mirror this type definition. So here's an empty here. We have to check when this list is empty. Otherwise, we have to take apart the list, right? Get the string out, which is this first. And otherwise, there's the self-reference over here. All right, so the code structure mirrors the data definition. And those are the two ingredients you need to design a proper list. You need a distinct value, empty or something, to mark when the list should stop growing, right? Mark the end of the list. And you need to have a self-reference to grow the list itself. So with that out of the way, let's just imagine hypothetically that Racket never gave us the empty list, or cons, or first and rest, and empty, How would we go about designing our own recursive data type that represents the idea of a list? Well, we would do something like this, right? Let me copy and paste this off to the side to save some time here. So what we would do is we'd make a link, and we would have an empty link to represent empty. And this make link represents the cons, right? This would be the cons equivalent. And this would be the string equivalent, right? A list can hold any type. And this would be the self-reference. So link is one of either this. So this would be link of something, but I just put link for short. So this would be the self-reference that allows it to grow. And this would be the empty that tells it to stop, all right? So we would define these with structures. So define struct empty link. It has no fields. And this is equivalent to the empty list. We can make it by make dash empty link. No fields, right? So it's equivalent to empty, and this define struct link is equivalent to cons with a first and rest. And you have to give it a link like so. Link dash first will get the first of the link, and link dash rest will get the rest of the link. So it's similar to the built-in list functions over here. All right. So this is how you would make a one element list, quote unquote. We'd make a link with 8 and then put it on the empty link. So you can imagine this with cons, and this would be empty list, right? It looks very similar. Likewise, the two element list, you just chain links together, make link of 8, and then chain that onto make link of 2 onto the empty link. And the template is also very similar, like so, right? We do something when the list is empty. Otherwise, we take apart the first and we do a recursive call on the rest. So here we take the empty link, we ask if the link is empty. Otherwise, if it's not, we take apart the first link and then we do a recursive call on the rest of the link. All right. So the entire point of all this is to demystify the idea that the built-in Racket list types, so Racket gives us empty, they give us cons, they give us empty, first, and rest. We want to demystify this as some black box thing that just comes from Racket and that we just use, and that we're just doomed if Racket never gave us a built-in list type. That is not the case. We can design our own recursive data types that behave the exact same as the built-in list data types over here, except it takes a lot more typing, right? We have to type link dash first and link dash rest instead of just first and rest. All right. So designing our own recursive data types is something that we will be exploring a lot more in the upcoming sections. All right. So let's explore the idea of other recursive types. So natural numbers can be thought of as a recursive data type. So I'm going to copy and paste this down. So natural is one of either 0. So this 0 is equivalent to the base case of empty here. Otherwise, we add 1 onto natural. So add 1 is just short for plus 1. All right. And we have a self-reference from natural to natural here, just like we do with list of string to list of string, right? All right. So this is interesting because we can write numbers like this. So to find 2 is going to be add 1 on the add 1 of 0, right? This is going to be the base case, right? This is similar to how we build lists, right? So define L2, right? So we have a 2-element list, cons 1 on the cons 2 empty, all right? So this add 1 is going to be equivalent to the cons. This 0 is equivalent to empty, all right? But beyond that, it is more useful when we think about the template over this, over natural numbers, right? Functions over natural numbers is a common problem that you'll see in the upcoming exercises. So we have natural temp, and it consumes the natural and produces something. This is just a template, scaffolding things out of functions that operate over natural numbers. And this is checking the base case, right? This is the equivalent to checking if it's empty, right over here, right, with our list template. If it is, we do something. Otherwise, we take it apart and then we call natural temp with sub1 of n. So this sub1 of n, it can be thought of as rest, right? So rest over here, right? The list gets smaller, all right? So like so. So the idea of recursive data types is very powerful when we stretch it to think of natural numbers as this recursive data type. Again, because this will help you solve some of the upcoming exercises if you think of natural numbers as a recursive data type over +1 natural. All right. In the upcoming sections, we're going to be modeling more complex forms of recursive data types, one of them being trees. So let me copy and paste this graph here. 1 second. This is a family tree. And how would we model this in code? Well, these are people, right? So Carl, Adam, Dave, and etc. So we're modeling people essentially. So let's do something like define struct person. All right, these people have names: Carl, Adam, Dave, Eva, right? So they have a name field. What else do they have? They have the birth year, 1967, 2000, 1977, so birth year. They have eye colors, so red, black, blue, pink, brown. All right, so eyes. And they have a mother and father. So Dave's mom is Bettina. His dad, following these arrows, is Carl. Eva's dad is Carl. And Eva's mother is Bettina. And like so. So let's do a mother and father field. All right, so what are the types for this? Well, person is make person. So the name is a string. Birth year is a number. Eyes is an eye color, which is represented by a string. Mother and father, what are these two? Well, let's start here with Dave. The mom is a person, right? So it's another person. And the father is also another person, all right? So this is an example of designing a bad recursive data type, because person, this does have a self-reference, right? So it goes like this, right? There are two self-references. That's not a bad thing, right? We're going to see that the upcoming data types will have two self-reference types. But the problem is that it's going to recurse forever. We don't have the base case over here, right? Like 0, all right? So if we do this, we're going to have to define a person's parents whose parents have parents whose parents have parents forever. And there's going to be no end. Eventually, you need a base case. You need to say, hey, we need to stop. Either we have no more information about the family. In case of Fred, right, we don't know who the mother and father is, right? So we need a base case, all right? So, yeah, we need a base case when designing recursive types, right? So, like empty here, like make empty link here, and like 0 for the natural number. We need a base case for this data type if we want to properly model a family tree. So we need to make this a comment. A family tree, call it FT for short, is one of, the base case can be any other value, right? It could be false, it could be it just has to be unique. So let's just pick false, right? And then make person over here. All right. But instead of person, we're going to say it's a type of family tree. All right. Like so. All right. Going to space this downwards. Now we have a stopping point, right? So for example, if we want to model Fred, right, who has no parents information, we can do something like define Fred to be make person. All right. So make person. Fred is the name. The birth year is 1978. Eyes are pink. So pink. And then father and mother are false because there are no arrows. As you can see, there are no arrows pointing up, right? And that allows us to stop, right? Likewise, Carl and Bettina, right? We don't have information about their parents, like so. So this is the very most important case here, right? Don't forget your base case. You need to have a stopping position along with the self-references. Otherwise, we're going to have to be looking for this guy's ancestor forever. All right.